Hello. In this video tutorial, we're going to take a look at waves graph practice. Please remember to pause or rewind the video as necessary. In this lesson, we're going to learn how to take a wave graph function, in this case, a position versus time function, and we're going to be able to sketch where the object is at time equals 0 seconds, find its period of oscillation, its frequency, its amplitude, the spring constant of the spring. We will also be able to determine the potential energy stored in the spring at maximum amplitude. We'll be able to find the maximum speed. And if we change the mass to anything else, we will be able to find the new period and the frequency of oscillation. Finally, given the position time graph, we will be able to sketch a graph of the velocity versus time function and the acceleration versus time function. So let's begin. Again, please remember to pause or rewind the video as you need to. Below is a graph of position versus time for a 100-gram block undergoing horizontal oscillations. So we have a horizontal oscillator at the end of a spring. Answer the questions below about the spring mass system. Draw a sketch of the spring system showing where the block is in relation to the equilibrium at t equals 0 seconds. Well, you should be able to tell from the picture that here's the equilibrium right there in the middle. And you can see there's an amplitude of 4 centimeters. We can actually kind of answer that right now. Go down to part 4. The amplitude is 4 centimeters or 0.04 meters. Okay, so we could actually draw a sketch of this. So I'm going to draw a wall. I'm going to draw a horizontal surface. I'm going to let x equal 0 here. I'm going to let x equal positive 4 centimeters over here. And I'm going to let x equal negative 4 centimeters over there. At time equals 0, the block is at 4 centimeters. I should be able to stretch it all the way out, and the block would be placed right here at time equals 0 seconds. What is the period of oscillation? Well, to figure out the period of oscillation, what we can do, the period t would be the time divided by the number of cycles. So what we can do is we take our graph and let's figure out, first of all, let's figure out how many cycles there are. Okay, so we've got, in this case, we're starting up at the top. The wave starts up at the top. So it would be, okay, so 1 cycle. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cycles in 10 seconds. Or we could say it's 10 seconds for 12 cycles. Now, you could have done this another way too. You could have gone 1, 2, 3, 4, 5, 6 cycles, 5 seconds. So I could have gone 5 seconds for 6 cycles. Notice this is just a reduced version of 10 over 12. Go ahead and divide those two. 10 divided by 12 would be 0.833. I'll just say 0.83 seconds. So it takes almost 1 second for a cycle. And you can see that right here. That matches up with about 0.83. Okay, now to get the frequency can be done one of 2 ways. We can take the total number of cycles and divide it by time. So you could just flip this and go 12 cycles over 10 seconds, which is 1.2 cycles per second, or 1.2 hertz is a more appropriate unit of frequency. Now, you could have also gotten this by taking frequency is equal to 1 over the period and just simply take the inverse of 0.83. 0.83 inverse, well, that gives you about 1.2. What is the spring constant for the spring? There's a couple ways we can figure this out. I'm going to show you two possible solutions for this. One, for a spring constant, the period for a spring, for an oscillating spring, is 2 pi times the square root of m over k, which would be the same thing as 2 pi times the square root of k over m if I just rewrote it as the division of the reciprocal. What that means is 2 pi over omega, well, that means omega is equal to the square root of k over m. What we can do is we can take that equation and we can solve it for k. So t is equal to 2 pi times the square root of m over k. Well, what I'm going to do is I'm going to square both sides. Okay, and if I do that, I get t squared equals 4 pi squared, and then square just eliminates the square root, m over k. To solve for k, just go ahead and switcheroo, and we get k is equal to 4 pi squared m over t squared. So now this value here, 4 pi squared, is about 39.5, roughly. Okay, multiply that times the mass, which was 100 grams. So 0.100 kilograms. Got to turn to kilograms. Divided by the period squared. Well, the period, if you remember, was 0.83. So about 0.83 squared. So we're going to go 4 times pi squared. And we're going to multiply that times 0.100, and we get about 3.9478, something like that on top, divided by 0.83 squared. It's roughly about 0.6889 on the bottom. So the spring constant, we're going to go 3.9478 divided by answer, and we're looking at roughly about 5.73 newtons per meter is our spring constant. How much elastic potential energy is stored in the spring at maximum amplitude? Well, elastic potential energy or spring potential energy, the equation for it is 1/2 k x squared. Now at maximum amplitude, we would write it as k a squared. So it's 1/2 times 5.7 newtons per meter, that's our k that we just found, times our amplitude of 0.04 meters squared. So we're going to put this part in first, we're going to square it, times by 5.7, and then take half. .04 squared times 5.7, that would be k, divided by 2. So we're looking at roughly about 0.00456 joules. Okay, now if you go back to the picture, what that means here, guys, is that the maximum potential energy, U max, at amplitude is 0.00456 joules right here at this moment. But what that means is as the block passes through the equilibrium position here, right, the spring is shorter, you now have all the maximum potential energy has converted into maximum kinetic energy, which if energy is conserved will be the same amount, 0.00456 joules. So the maximum speed, first of all, we know the maximum kinetic energy is the same, 0.00456 joules. We know that kinetic energy is equal to 1/2 mv squared. To solve for speed, we need to multiply by 2, divide by mass, and square root. So 2 times the kinetic energy divided by the mass, then we will square root. So 2 times 0.00456 joules, divided that by 0.100 kilograms, and then we will square root. So times 2 divided by 0.100 square root. And the block is moving at about 0.302. I'm just going to round that to 0.30 meters per second. 0.30 meters per second. Now, if the mass is changed to 250 grams and the same spring is used, same spring means same spring constant K, right, of 5.7 newtons per meter. Determine the new period and frequency. So the period of a mass spring system is 2 pi times the square root of m over k, but you've just increased the mass by 2.5 times greater. So let's figure that out. 2.250 times 5.7. So we're going to go 0.250 divided by 5.7, take the square root of that, and then multiply that times 2 pi. And we get roughly about 1.32 seconds. Now, why does that make sense? Because according to this model, t is proportional to the square root of the mass. So if the mass is 2.5 times larger, what is the square root of 2.5? The square root of 2.5 is roughly about 1.58. So if we take 1.58 times the original period, which is 0.83, you get 1.32, right? It's another way of getting that value. So you could have done this using kind of a relative proportional reasoning analysis, or you could have actually plugged in numbers. Either way, you can get that. Now, how do we get the new frequency? Just inverse the new period. So the inverse of that would be about 0.76 cycles per second, or 0.76 hertz. Okay, now on the back side, what we're going to do is we're going to plot the velocity versus time function and the acceleration versus time function. Now, to figure out the acceleration, the max acceleration, well, here's what we have. Net force, whoops, we're going to do this down below. Net force is equal to ma, but net force is also equal to kx, because we're talking about a spring force. So set those two equal to each other, and we have ma equals kx. Solve for a max is going to be ka, where x max is the amplitude, divided by mass. So we can figure out a max right on the spot. That way that'll help us plot the amplitude of our acceleration function. So we're going to go 5.7 times the amplitude, which if you remember was 4 centimeters or 0.04 meters, divided by the original mass, which was 0.1 kilograms. So we're going to go 5.7 times 0.04, divide that by 0.100, and we're looking at about 2.28 meters per second squared. That's our largest amplitude for acceleration above and below equilibrium on this graph right here. Okay, so we'll get to that. If you remember, our maximum velocity was 0.3. So we could actually plot that by going 0.1, 0.2, 0.3. Negative 0.1, negative 0.2, negative 0.3. For our final graph, I could use a scale that goes 1, 2, 3. Okay. Oh, keep in mind, I'm sorry. This is centimeters per second. I almost missed that. Okay, so I can fix that by going 10, 20, 30 centimeters per second, negative 10, negative 20, negative 30 centimeters per second. Here, we're going to go 100, 200, 300, negative 100, negative 200, negative 300 centimeters per second squared. So this answer here would be 228 centimeters per second squared. Keep that in mind. You have to move the decimal over a couple times. Okay. So that means that this answer of max velocity is actually 30 centimeters per second, which is what we're going to be plotting in a moment. Now, what's important about this graph is, if you recall how this works, if we start with, we're starting at the position, the amplitude position. So that is a positive cosine function. So x would be a cosine omega t. That means v, the velocity graph, would be, you're going from a cosine function to a negative sine function. So negative a omega sine omega t. Okay, where a omega is your negative 30. That's your plot. So it's good, but it's going to repeat as often. It's just going to be a negative sine function. So to plot the velocity function, which is a negative sine function, remember a negative sine function would look like this. We're basically going to start at the equilibrium position, and notice every 0.83 seconds is roughly when we have to repeat again. So I'm going to make a note of when we have to repeat. We have to repeat again right here. I'm just, what I'm really doing is I'm just going straight down like this. Straight down, straight down. Okay, so follow how often it repeats. Just go ahead and make a dot about every 0.83 seconds or so, like I'm doing. Okay, that is telling you it's going to go through one full cycle. Okay, so what that means is it's going to look like this. Down, up, and then back again. So we're going to make this a lot cleaner by showing you that I'm going to make a blue dot in the middle of all those black ones. That's showing you when the wave is going to change direction. Again, I'm just putting these dots here to give myself reference. This really helps. Okay. Now I'm going to go halfway. I'm going to use a red dot. I'm going to go halfway here, and I'm going to go all the way down. I'm going to make a dot here. I'm going to go halfway here. I'm going to make a dot all the way up here, just like that. It's going to help me stay focused with my wave. Now you don't have to do it this way, but it'll keep it looking a lot nicer. So the graph ought to look like this. Down, up, down, repeating again. Up, down, up, down, all the way down, up, 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 and then down again. Okay, it's not perfect, but what it tells you is the amplitude is fairly constant at about 30 and -30 all the way across. Okay, and the wave repeats itself about every 0.83 seconds. Okay, so it keeps the same period. Finally, in the acceleration versus time graph, you're going to be plotting about 228. So 228 would be about a quarter of the way between 200 and 300. So there's 250, there's 225. 228 is just a little bit higher than that. So I'm going to make a dashed line all the way across like this. That way I can keep my amplitude constant for this acceleration graph. I'm going to do the same thing down here at -225, which is pretty close to -228. Make a dashed line all the way across. That way we can keep our amplitude constant. Now, what are we graphing here? Well, you're going from a negative sine graph. The acceleration function is going to be going from negative sine to negative cosine. So negative a omega squared cosine omega t. Okay, where a omega squared is your 228 and -228. It's your amplitude. So a negative cosine function is what we're plotting. If you recall, a negative cosine function starts down at the amplitude and looks like this. Okay, that's the sketch that we're plotting. So we're going to repeat this every 0.83 seconds. So let's go to the graph, and we're going to go start down here. And we're going to repeat this but every 0.83 seconds. So again, I'm just going all the way down, all the way down, all the way down. Everywhere I had those black dots before, I'm keeping the same spacing. 0.83, 0.83, 0.83, 0.83. You're right at 5 seconds. 0.83, 0.83, 0.83, 0.83, 0.83, and then you're right at 10 seconds. There we go. Okay, and then what I'm going to do is I'm going to make a blue dot halfway. So I'm going to go halfway and go all the way up here and put the blue dot right there. So halfway, halfway, and so forth. So I'm just going to repeat that over and over and over again. And that will at least get me focused on what the graph should be. I don't need to keep making the blue dots. It's just making me focused on what the graph should end up looking like. It's going to look like this. I'm going to go up, down, and repeat again. Up, down, 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 up, and finally back down again. And that would be a graph of your position, velocity, and acceleration as a function of time. Notice the amplitudes are all different, but the periods are identical. Therefore, the waves repeat exactly as often.